Hey guys, my name is Devin. My YouTube channel is DRG Bros. Today, we don't exactly have much of a set topic for this video. What we're going to be doing is we're going to be using some identities to solve some problems. So first off, quick review. So, what is an identity? So, an identity is something that has been proved off of something we already know. If that makes sense. So, like, an example of an identity could be the cosine squared of theta plus the sine squared of theta equals 1. And what we can do with identities is we can turn them into new identities. So, for example, to finish this one off here, if we divide everything by the cosine squared of theta, we end up with 1 plus the tangent squared of theta equals, and then we haven't talked about this one much in these videos, but the secant squared of theta. So now a couple other ones real quick. So if we have, say, a plus b squared, like this, then we know that that's equal to a squared plus 2ab plus b squared. Right, sorry, I forgot to mention this. Keep an eye on these two, because these are going to be useful throughout what we're doing today, just through some of these problems. If we have the natural log of x to the n power, we can write that as n to the natural log of x. One more quick one. We talked about this in a couple of our videos. Any polynomial can be factored out into smaller little bits. So if we have, say, 2 over x squared minus 1, this is a pretty close example of what we're going to be doing in one of the problems today, equals 2 over x plus 1, x minus 1, which we know is equal to negative 1 over x plus 1, plus 1 over x minus 1, sorry guys. Wait, hold on, no. Wait, yes. Yes, this is positive, and that's, okay. Sorry, I'm getting confused with my own problem here. Okay. Next, we're going to talk about the product rule. So what this means is if we want to differentiate f of x, g of x, first thing we're going to do is we're going to write two copies, f of x, g of x, plus f of x, g of x. And then what we're going to do is we're going to make the first one in the first one prime and the second one in the second one prime. So I'm sure some of you viewers already got it by now, but for those of you who don't, I'm going to do another example. So if we have d over dx, f of x, g of x, h of x, what's that equal to? So first we're going to write it 3 times. F of x, g of x, h of x, plus f of x, g of x, h of x, plus f of x, g of x, h of x. Then the first one's prime in the first one, the second one in the second one's prime, and the third one in the third one is prime. See? So now we're going to solve a problem here. Kind of a warm-up problem, and it's going to be using this identity right here. You got to keep that one in mind, guys, because that one's going to be a huge help to us throughout this video. So the problem that we're going to be solving is d over d theta tangent of theta. Okay? What is this equal to? So we saw in that rule that I told you to keep in mind, that first part of it, with the division, we know that we can rewrite this as d over d theta sine of theta over cosine of theta. And it's not going to be squared because there's no squared here, so yeah. So then what we can do is we can separate this so we can have d over d theta and we're going to use brackets here. Sine of theta, cosine, and technically it's proper to put parentheses around the theta, and we're going to inverse that. So it's going to be the inverse of cosine theta. Then, what we're going to do is remember the product rule. When we differentiate this, we have sine of theta, cosine of theta, inverse it, plus sine of theta, cosine of theta, inversed. And then, according to the product rule, this first sign is prime. Yeah, and the second cosine is prime. So now it becomes a little more simple. Or, well, we have one more step and then it becomes simple. So what we're going to do, so if we differentiate the sine of theta, that's the cosine of theta. And then we still have the cosine of theta to the -1, to inverse, plus the sine of theta, because that didn't change. This is where it's tricky, okay? So you're going to have to stick with me here. The correct way to write this is to pull the -1 out, so -1 cosine of theta to the -2 power times the inverse, which is negative sine of theta. Alright, that's the right way to write it. So then what we can do is, there's a rule where if this is inverse, we can divide it and like keep the power. So you see, so if you have a negative exponent, I'll explain this over here. If you have a negative exponent, so say x to the -3, what you can do is you can rewrite this as x over x to the 3rd power. So that's what we're going to do here. We're going to do the cosine of theta over the cosine of theta to the 1st power plus this is going to be the sine of theta over, or sine squared of theta, right? Yeah, the sine squared of theta over the cosine squared of theta, because, like, yeah, we have this, and then this negative makes this a positive, which means these two make the sine squared, and then this, because of the positive, turns into the cosine squared. If that makes sense. And remember from the very beginning that this is now 1, because this is divided, plus the tangent squared of theta. And one more step is, remember the first rule, the secant squared of theta. And I want to point out, this answer is still technically correct, and you can, like, show this in and this will be correct, but this is the more professional answer, is the secant squared. So next we're going to go back to our old friend polynomials. And these are not that bad, I'll be honest, because they're very simple. So we're going to start with this case. So integral r of x dx, okay? Now, if r is a rational expression, then we can rewrite this as the integral of p of x over q of x. And I guess technically you can use whatever variables, I guess, dx, where p and q, like p of x and q of x, are polynomials. So, for example, we could have something like this. So p could be 5x squared plus 7x minus 3, and q could be 8x cubed plus 6x squared plus 9x plus 2 dx, okay? And this is a very easy problem for us to solve if we wanted to. Now, yeah, again, these are special cases. The general problem, I'll just write this out for you. The general problem would be the integral of, we're going to use a, m, b, and n for this, okay? So a, m, x to the m, plus a, m, minus 1, x to the m, minus 1. And m is like the exponents. Yeah, so m is the exponents, and that keeps going until our final variable, which is a1, x to the first, plus a naught. All over, pretty much the same thing, but with b and n. bn x to the n, plus bn minus 1, x to the n minus 1, all the way to our final one, dot, 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 b1, x to the first, plus b naught dx. So this is actually a very simple problem. So now I'm going to give you, I think, our final two problems of the video. So I want you to consider the difference between the integral of 2 minus x squared minus 1 dx and the integral of 2 over x squared plus 1 dx. Not much of a difference there, right? But can you find what's so difficult about this one and different about this one than this one? Well, let's see, because this one, we already know the answers as x plus 1, x minus 1. But what about this one? Now, there's an x squared, which means we have to have two x's, so x and x. And we have two 1s, so we know that the other two have to be 1 and 1. But are they negative or positive? Well, the answer is neither, because think about it this way. If we have the x's, they both have to be positive, right? Because of plus 1, or negative. If they're both negative, it's x squared minus 2x plus 1. And if they're both positive, it's x squared plus 2x plus 1. So what do? Imaginary numbers and complex numbers. So x plus I, x minus I would be how we were to technically solve this. So this is much harder to factor. Now this top one, I'm going to start in the calculations here. We're going to solve both of them. We're going to just solve the top one first. And believe it or not, the first one may be easier to factor, but believe it or not, the second one's actually quicker to calculate. The first one's easier, but the second one's quicker, believe it or not. But you'll see. So, I'm going to just rewrite it up here. So we have the integral of 2 over x squared minus 1 dx. Now, how are we going to solve this? Well, notice we can't use a u substitution. Why? I'll give you a moment. Okay. The reason we can't do a u substitution is because with the x squared, when we differentiate it for du, the x's will be uneven in the final problem, and it won't work. So what we have to do instead is to use our good old method of partial fractions. So what we're going to do is we're going to take the problem, and as you saw, we're already going to split it. So x minus 1, x plus 1, dx, which is equal to the integral of 1 over x minus 1 plus negative 1 over x plus 1. And I just know this. If you really wanted to prove it, you could go and watch one of my videos on partial fractions where I explain how to do it. And you can go through this and watch the proof. And you can actually make the proof yourself, because this is not very difficult whatsoever. I could probably solve this in another couple of steps, but to save time, we're just going to say it's this because there's still quite a bit more. So the first thing we're going to do is we're going to split the two apart in separate integrals. So it's going to be the integral of 1 over x minus 1 dx plus the integral of negative 1 over x plus 1 dx. And then we're going to solve each one separately. But now, notice that there's only one x. So guess what that means? We get to do a u substitution. So let u1 equal x minus 1, u2 equals x plus 1, and you'll notice both du's, du1 and du2, are both just going to equal dx. See, 1 dx, because, yeah. So then we're going to fill those back in, so it's going to be the integral of 1 over u1 du1 minus the integral of 1 over u2 du2. See what I did with the negative? I moved it to the front. So this becomes a natural log. So this is equal to the natural log of u1 plus c1 minus the natural log of u2 plus c2. So what we can do is then we plug the u's back in, and we get the natural log of x minus 1 plus c1 minus the natural log of x plus 1 plus c2. And this is technically a correct answer if you want to go with this. The more professional way to do it, you add the c's together. I don't know why I'm losing it. So instead of just the c's, you just subtract it and then plus c, because you can put them both together. I'm sorry, I forgot that. So that's technically the answer, if you want that to be the answer. However, there's a rule, like an identity, that the log, I'm going to just use x and y here, the log of x, natural log of x minus the natural log of y equals the natural log of x over y. I don't know why I wrote log, that should be the natural log. So what this means is the professional answer would be the natural log of x minus 1 over x plus 1 plus c. And that is the best answer for this problem. Now, for the final bit of this, it's almost done, guys. The final bit of this problem is we're going to solve the other one. So, the integral of 1 over x squared plus 1 dx. And how we're going to solve this one is using change of variables. And what are we going to change the x and dx into? You guessed it. Our old friends tangent and secant. So let x be equal to the tangent of theta, and dx is going to equal the secant squared of theta d theta. You got to pick your integrals carefully, because if you don't pick them right, then the whole problem's going to go off. And why not just normal secant? Well, there's the squared, so this is going to become, down here, the tangent squared. So it's going to make our life easier. So the integral of 1 over the tangent squared of theta plus 1 secant squared of theta d theta. Now, if you remember our rule, this is equal to the secant squared of theta. So I'm going to write that out. Secant squared of theta, secant squared of theta d theta. These two are going to cancel out, and that just leaves us with the integral of d theta. And whenever you have an integral and dx or d theta or dy or whatever you have, the integral and the d essentially cancel each other out, and you're just left with, in this case, theta. Now, remember, however, that at the beginning that we let x equal the tangent of theta. Well, if we move the tangent to the other side, and we have the inverse of tangent x equals theta. So then the correct answer is the inverse of the tangent x. I don't know how to say it. That's the answer. So thank you guys very much for watching this video. I hope you enjoy it, and I'll see you for another video. Yeah, bye guys.